In the last couple of videos, we looked at what it means for a real signal x of t to be even or odd. Now, there is a similar notion of symmetry when x of t is a complex signal, and we call such a notion as conjugate symmetry. Okay? So, if let's say x of t is a complex signal, and in Cartesian form it's given as a of t plus j times b of t, where a of t and b of t are the real part and the imaginary parts. Or in polar form, let's say it's given as r of t times e raised to j times theta of t. Now, the equivalent notion of an even signal is that of a conjugate symmetric signal. So when x of t is complex, we don't call it as an even signal, rather we call it as a conjugate symmetric signal. Well, what it means, a signal is conjugate symmetric if x of t is equal to x conjugate of negative t. Okay, notice the conjugate here. The definition does not say that x of t is equal to x of negative t, rather it says x of t has to be equal to the conjugate of x of minus t. Then we say that x of t is a conjugate symmetric signal. And similarly, we say that x of t is conjugate antisymmetric. Conjugate antisymmetric if x of t is equal to the negative of x conjugate of minus t, or equivalently, this also implies that x conjugate of t is negative of x of minus t, or negative of x of t is negative of x conjugate of minus t. Okay. Now, you may wonder why we have to define a signal, the equivalent notion of symmetry using conjugate symmetry. Why not just define a signal that satisfies x of t is equal to x of minus t as the complex counterpart of an even signal? Well, unfortunately, at this point in the course, I cannot give you a good motivation for this. Later on, you will read about Fourier transforms, or if you have already read about Fourier transforms and you're watching this video as as a review, then you may be able to appreciate this. And this has to do with the fact that it's really this complex the conjugate symmetric signal which has certain properties which are similar to that of even signals in how their Fourier transforms are related. So particularly what I mean by that is this: if x of t is real, then it turns out that the Fourier transform of x of t is conjugate symmetric. Okay. Suppose x of t is real and even. Then it turns out that the Fourier transform of x of t, x of j omega, is real. Or in other words, if it's even, x of t is even, then x of j omega turns out to be real. So then you can ask the natural question, if x of t were complex, then what property should x of t have such that x of j omega is real? Okay, and this turns out to be that x of t has to be conjugate symmetric. It's not enough for x of t to be equal to x of minus t, but it turns out that x of t has to be equal to x conjugate of minus t. Only then x of j omega is real. So the point is if x of t is real and even, it has the same properties as a complex x of t if it is conjugate symmetric in the Fourier domain. Okay, and this is why evenness is the same as conjugate symmetry and odd is the same as conjugate antisymmetry. Okay, now we defined a conjugate symmetric signal as one for which x of t is equal to x conjugate of negative t. Now, what does this mean in terms of the real and imaginary parts of x of t? Well, if x of t is a of t plus b of t, I'm sorry, j times b of t, then the above expression means that if I plug in t is minus t and then take the conjugate, I get a of minus t minus j times b of t. Now, if the left hand side has to be equal to the right hand side, it means that a of t must be equal to a of minus t, but b of t must be equal to negative b of minus t, or a of t is real and a of t is even and b of t is odd. Now, in the same way, you can see that if you think about x of t in polar form, then the condition that x of t must be equal to x conjugate of minus t must mean that r of t times e to the j theta of t must be equal to r of negative t times e to the minus j theta of negative t. The minus j comes from conjugation, which actually implies that r of t must be equal to r of minus t, or r of t is even, and theta of t is negative theta of negative t, which implies that theta of t must be odd. Okay. In the same way, you can derive the conditions for the real and imaginary parts when x of t is conjugate antisymmetric. And you can see in this case, what's going to happen is that you need to get the condition that a of t is odd and b of t is even. Okay. Now, the definition of a conjugate symmetric and conjugate antisymmetric signals work the same for discrete time signals as well, and so I'm not going to explicitly talk about that, but all these properties remain the same. Okay.